uh, due, not too much to say today. Uh, Last month I made several observations of CFUS-A measure. Uh, here is results. Mm, uh, Not too much changes in the spectrum of CFUS-A, 6.7 gigahertz line. Uh, mm, Red shifted part is usually uh, higher than blue shifted parts during this month. I, I think I think this measure was quiet uh, last month. No, no, not as in some months where when it was very when it was variable, more variable. But the levels are calculated with system temperature 180 Kelvin. Uh, mm, I mm, there was some degradations in measurements of here in measurements of system temperature by Y-factor method. Uh, mm, uh, I see less Y-factor from 4.3 dB to 3.8 dB, and system temperature uh, up to 119 kelvins, uh, and so levels, peak levels about 50, 500, 600 Yansky was calculated at 180 kelvins of system temperature. But I this this degradations is not confirmed by when checking by other method of measurements system temperature. I used the moon radiation to estimate my system temperature. Uh, Here is a formula I used mm, mm, to estimate my system temperature, but it was obtained for uniform temperature distributions over the disk and not taken into account cosmic microwave background. Y factor is measured when antenna is directed to the moon immediately, and Y factor is calculated comparing uh, the receiver output when antenna is shifted somewhat outside of the moon. Um, um, I measured 0.4 dB of Y factor for the moon. This is rather high Y factor, and for system temperature 118 Kelvin, and even for my previous system temperature 150 kelvins, and best fit for this Y factor, this moon Y factor is 120, 130 Kelvin and no more. Also, I measured noise figure for LNA, my LNA to check is its degradations, its noise degradations. It was almost the same as for a fresh new as I measured it in in uh, uh, in this May, its noisy figure is about 1.2 dB and almost no degradations. So I wondered that too much uncertainty in system temperature measurement from 120 kelvins up to 119 kelvins is very high range of uncertainty in system temperature measurement. So the levels of peak levels for measured peak levels for measure may from 600 K from 400 kelvins up to 700 400 Yansky up to 700 Yansky only due to range of uncertainty in system temperature measurements. This is all for now. Thanks.
Okay, questions for Dmitry. It's really good. I've never seen the T-moon measurement before.
Maybe I have one or two questions slash comments. I think one of the uncertainty in your T-systems measurement with the brick wall is, of course, what is the temperature of the brick wall? I think you took ambient temperature minus some 10 degrees or so. But of course, this is an assumption. So maybe actually the brick wall is not as warm as you think. I mentioned this because we had a similar experience that when we compared a wall against a real absorber, we found that the wall was deviating from being a black body radii at ambient temperature. This was at L band though, so maybe it's cannot be directly compared to the S band or where you are. The other, that's a question that I have. In your formula about the moon, you had the aperture efficiency of your disk as one of the parameters, and you assumed an aperture efficiency of 0.85, which seems fairly high for a parabolic dish. So is that something that you assumed, or is that something that you have measured?
Yes, main beam efficiency was estimated 0.85.
Okay, so this is an estimate.
This is an estimate, but estimate from well, from calculated aperture efficiency was calculated about 0.64 and This estimate is under assumption that aperture efficiency and main beam efficiency is connected for and I obtained these connections for Gaussian beams, and I describe it this connection since in this paper, if you if you I can share the reprint if this journal is hardly available. Just ask me, or I can share in this paper in the chat. It's okay?
Yeah, thank you very much. Thanks.
Mhm.
Any other questions, anybody? So are you going to be taking more moon measurements, and how much, based on the phase of the moon, the distance of the moon from the Earth, how much does that the T moon vary? Do you know?
In phase for 7.7 gigahertz, the temperature of the moon is changed. There are minor changes in temperature of moon temperature for this frequency. Changes with phase is more noticeable for 10 gigahertz and higher, and but I suppose that 6.7 gigahertz changes is almost no changes in this frequency and temperature from the moon was taken about 230 Kelvin for all phases. And other assumptions that temperature is distributed over the disk uniformly, and so the possible distributions also not take account. More accurate formula. So you can see in this paper, I could share in the chat now. So you can see this procedure for more measurements in more details.
Okay, great. Well, this is good stuff.
Okay, Richard, maybe a comment to your question. I think the understanding is that the radio emission from the moon comes from lower below the surface, and it is lower as the longer the wavelengths get. And actually, in L band, you don't see any difference between new moon and full moon, and it becomes noticeable, as Dimitri has said, in when you go to KU band. But I would agree that at 6.7 gigahertz, there's probably only a minor variation of the moon temperature or the emission temperature of the moon, whether it's new moon or full moon.
Okay. Is this something with that we can measure with the at 1.4 gigahertz? Does that be worth doing?
Yeah, I mean, the moon has at L band, it has a flux density, if I recall correctly, of 900 Jansky. So it is quite visible with your antenna. It should be easily visible. With smaller antennas like a 3-meter dish, it becomes a bit of an exercise, I would say, but still, it's possible.
Okay.
Wouldn't keeping your dish aimed at the moon be important also?
Yeah, sure. I mean, depending on the size of your dish, you need to track the moon. Yeah.
Mhm.
Okay. All right. Really good. And yeah, this the other frequency, since we were doing moon bounce at our open house at our 60-foot dish, so they were tracking the moon full time, and I guess we could just at 12. They were using 1260 megahertz. That might be. That's probably a possible one, just to go and measure that. Okay. And the other thing, just to let you know what they were doing, is we were timing they had an oscilloscope on there, and they were timing how long it took for the bounce to come back, so they could figure distance. So that was a fun one. Okay. Anything else for Dimitri?
Okay, thanks.
Thank you very much. And is the weather getting colder up there? I know that's a picture in your backyard, but in the winter, but I don't know how cold it gets this time of year for you guys. Oh, okay.
Okay, thanks, Tom.
Okay. All right. Hey, thank you. Very good. Wolfgang, what do you got?
Maybe two things to mention. We had the Yukara conference. Was it last weekend or even the weekend before? Yeah, last weekend. No, the weekend before last. Okay, 2 weeks ago. We had 40 some participants locally, and a couple of, maybe a handful, 6, 7 online. Of course, we very much appreciated having people with us. We had talks in the morning on Saturday. Actually, we already had a sort of an informal session on Friday when people were coming in, and we were discussing things, doing experiments and stuff. Saturday morning there were contributions, talks. In the afternoon we went to the Effelsberg telescope, visited there, and on Sunday again we had talks in the morning, and in the afternoon there were essentially tours at our facility showing the different instruments and so on. It was really great fun, and really appreciated people being there. The slides from the various presentations will be made available hopefully soon on our website, and I'll send out a note once that is done. So we're just collecting the permission from different people. So yeah, I really enjoyed having the conference. I'm also happy that I can hopefully that will take place this time. The next Yukara will be in 2 years, and it will be in the UK. So the guys in the UK are now planning that and arranging things. We were hoping already to have it this year, but it didn't quite work out. So they are now offering to host a conference in the UK in 2025. Okay, other than that, we had some discussion on the forum about interferometry, and I just want to share with you some experiments that we did. Let me just share my slide. Okay. Make that full screen. So is that visible to everybody?
Yes.
Okay. I call this poor man's interferometer. It was a little exercise to say, can we make an interferometer with very too little simple antenna. So we took two cantennas, or what we always built them from stovepipes. That's why we call them a stovepipe antenna. It's essentially a circular waveguide with 15 centimeter diameter. And then there's a LNA attached to it. And we put it on a tripod just to have it somehow fixed. And we put it at two baselines. One baseline was 15 meters and another one was 30 meters. But actually 30 meters is a bit too much for the sun at L band. So 15 is really a better way. What else do we have in the RF chain? We had a cavity filter, about 40 megahertz of bandwidth in the L band, around 1400 megahertz. And we use a Lime SDR to do the correlation between the two antennas. The two photographs show the east and west antenna, sort of roughly directed to the sun. And well, this is the way the setup looks. In the foreground, there's our west antenna. In the background, where the lady is, that's our east antenna. That was a 30-meter baseline. Later on, we took a shorter baseline. And the experiment was aimed at the question, can you see fringes with such simple antennas when looking at the sun? And indeed you can. So this is a recent recording of some time. Of course, the fringes stay on for a long time because these antennas have a very wide opening angle. So you only need to direct them very roughly and you'll get the fringes. So this is just a quick experiment that I wanted to share with you. We're just analyzing things, and we found a few things to be looked into further. But just want to share with you saying, okay, if you have two simple antennas, you can actually do a small interferometer. Okay, that's all I can say at the moment about it.
The cavity filter is, what was the purpose on that?
Well, it was just to avoid interference from essentially out of band things. The reason why we introduced it, we had some spikes in there and said, okay, maybe that's some out of band interference, so let's put in the cavity filters just to be on the safe side. It seemed to reduce that, but I'm not sure whether that's really necessary, because you do have a confined bandwidth anyway from the SDR. Question though is what type of SDR to use, how well is it filtering? So we just put in the cavity filter. Another option would be obviously to take the no OLEG amplifier as an LNA, which has an integrated filter. That would probably work as well, but we didn't have two of them readily available, so we took the cavity filters.
And the frequency of this measurement was what?
It's 1400 megahertz, so we were just a bit below the hydrogen line.
Okay. So this is for a scope in the box setup. If we just give them, if we get another antenna with an LNA and plug that in, they could do that.
Yes, they could do that. The question then is what to use as an SDR. We use the Lime SDR, which has a dual channel input. My understanding is that it can also be done with two RTL SDRs if they are clocked from the same source. So you need to have an external clock, and there are some tricks to be done. Probably the expert on that is Marcos. He made a comment to that extent recently on the forum that you need to do certain things with the RTL SDR so you don't lose the coherence.
Now, would it work if you just put an RF splitter in there and have the two inputs from the antenna and then the output to the SDR? Would that work the same way?
Well, there are things. I think there are. I mean, you in theory you would get fringes, but this is on top of a strongly varying background. Using a correlator has advantages, so it suppresses all fluctuations. Whether that's possible just to do a that with a splitter. In theory, yes. Whether the signal to noise ratio is sufficient, then I don't know. There are other options like doing a phase switch interferometer. This would be another option, which is probably also workable. In our case, we just took what we had. We had the Lime SDR, we had the software. By the way, we use it's called Simple Correlator by Marcus Leach. That part is also now part of what he has distributed as a BAA software. So it's now it's in there, but we used the original one just because it was already on the computer. So essentially, the message is, if you want to have some fun with interferometry, you don't need to have big dishes. You can actually do it with these little things here.
All right. Okay, any questions? I guess one other question I had, and this is based on Ted's observation he was doing, does the beam width of the effective antenna, what would you consider that? Would you consider it the fringe spacing, or the what would you consider?
Well, the antenna has an extremely wide beam width, something like 90 degrees or so. It's looking all over the place. We can easily determine that. Today we did an experiment where we just let it sit, and we were continuously receiving fringes from the sun, even if the sun were nowhere near where the antenna was pointing. It was losing a bit of efficiency, of course, but that's actually the whole purpose of the exercise. The whole idea was triggered by in a university experiment where they're using Ku band antennas, and they have a hard time aligning the antennas when when the sun is not shining. If it's cloudy, they can't align it. So we said, okay, if you go to L band, if you're off by 20 degrees in your pointing, who cares? It's such a wide beam width. And the question for us was, is the sensitivity for such a small opening aperture, just 15 centimeter in diameter, is that good enough to see any fringes? And the question is yes, it works nicely.
Okay. All right, thanks. Any other questions for Wolfgang?
Thank you, Wolfgang. That's great stuff. I have an update on my system. It's probably appropriate to follow after that.
Go for it.
It's always dangerous. Let me turn this on. It's always dangerous to follow Wolfgang. Wow, but I'm going to give it a try anyway. Thank you, Wolfgang. That's exciting. I'm trying something even cheaper. Let me show you some pictures. This guy. So at the Eastern Conference, I'm hoping you see that, and I'll even do this.
We see it fine.
I introduced this idea of a very cheap antenna with just some wires on a PVC pipe. And there's more detail in my presentation, if we care. But they're so cheap that I made two of them. So I hooked up two of them pointing at the sun. They are spaced 2 meters, 2.0 meters apart. And so let's see what happened. I was looking at the normal hydrogen at 1420 and looking at all the signals. You see the blue signals at the top kind of go up and they go down. When you process it, the green one has one bump and another bump when the hydrogen went by. That's fine. But what happened here in the about noontime, all kinds of wiggles and strange bumps. So sure enough, the galactic crossings are where the vertical lines are. But when you process it, sure enough, here in pink, you can see a bump and a bump when hydrogen goes by. But wow, what about all these wiggles? So Ezra has a way to look at only certain samples. So I'm looking from here to here. Oh no, here's 24 hours of that sample, of that signal, pardon me. But let's look at just this part and zoom in on it. And it has nice wiggles going along here from interference from the sun. I think that's kind of neat. How many are there? They count up 1, 2, all the way up to 9. And that kind of matches the 9.5 wavelength spacing that is 2 meters divided by 21 centimeters. That's kind of interesting. What is the spacing between these fringe patterns? If you do some math, you can find out that it's 195 minutes, and you count up 8 different fringes along that way. So I've got a sample of about 24 minutes per fringe cycle. And with Rich's formula, that works out to be just about right. That formula said 24. Okay, good. What else can we do? Here's this funny shape that goes up and comes down, which is something related to the beam pattern of the antenna. How wide an area does that antenna actually receive from? And so if you look at that envelope, and it's kind of simulated with some lines here, it must be somewhere between those two places and these two places. And you find the peak value up here and the lowest value down here at the base. Halfway between those two, the average is this number in the purple line. And where does that envelope intersect? From here to there. If you do the math by stealing the time frame down here and moving it up, I find 149 minutes. Well, with 15 degrees of the Earth rotating every 60 minutes, that turns out to be about 37 degrees. But of course, after that, you have to subtract half a degree because the sun is not a point object. Okay, about 37 degrees for a bandwidth of an antenna that looks like that. That seems to be pretty consistent. And so that's my little interferometer. I will study more things. In fact, listening not to 1420.405, because now you get interaction for whether hydrogen's there or not. But I'm going to listen 3 megahertz higher, up at 1423, just so that I am listening only to the sun and its broadband spectrum of frequencies, instead of being distracted by hydrogen appearing and disappearing. So that's it. Oh, and the way, let's see how this hooked up. I have an amplifier right at the antenna on both of these. It comes down a 30-foot white coax you can see piled up all around the place. I tried to work with a TV splitter to put it down one coax to one SDR receiver inside. And that didn't work because I couldn't get the voltage to power the LNAs through that splitter. It said DC pass, but I disagree. It didn't work at the voltage that I was working at anyway. And so I simply took 3 F connectors and shorted them together, the outsides to the insides. So I'm shorting the 2 LNA signals after 30 feet of cable on each, and then running that inside. And then it seems to work. So much for a combiner. It's just shorting the signals together. And I hope the LNAs can survive. That's what I have. Questions?
Have you tried looking for Cygnus A and Cassiopeia A? They may be within range of actually seeing fringes on that.
That I'm going to work up to that part. I can find the sun. That's really easy. And I thought I'd play with spacing. Here's 2 meters. What happens to all that fringe stuff when I move to 3 meters or 4 meters? And then I'll move out, apparently not to 30 meters. You say that's kind of tough, Wolfgang. So maybe I'll go 15 meters.
Yeah, I think 30 meters is too much, because then the fringe spacing gets smaller than the diameter of the sun, which washes out the fringes. So it's, I think 15 meters is the limit where you want to go. You don't want to go further as long as you talk about the sun. When you talk about Cassiopeia A and so on, you can widen it if you like. But I mean, that's perfectly fine using 10 meters or so. But
Oh,
as you
that's
said,
very-
it's taking your 2 meter arrangement, making 3 or 4 meters, that should change your frequency, your fringe frequency as calculated. And I have no doubt that that will happen because that's physics. And I have no doubt that what you're seeing is actually the sun.
Neat. What's kind of interesting about this pattern, Richard will point out, is that we're adding and subtracting signals. How come it doesn't go below the 0 line here? Rich, you were saying that that's because we're looking at such a broad source as the sun. So
Now, I
I
think
thought that was interesting.
But I think that's it's what you're doing in terms of detection. You're looking at the total signal, which varies as the interference comes in. So it goes up and down, but never drops below 0. That's in contrast to what we are doing. We're doing a correlation. So we're essentially doing a conjugate, what is it called? Conjugate, anything. So we have 2 IQ signals and we multiply them. I1 times Q2 and the other way around. And that's a different kind of detection, which makes you independent of any fluctuations of the background and so on. So this is why you are seeing not something that is symmetrical going around 0, but it's going up from a 0, essentially a 0 line. But that's perfectly fine the way you do your detection.
So there's no negative power to add to my system. There's only an interference pattern of positive power.
Yeah, it's an interference pattern of positive power, whereas our is a phase angle measurement. We are measuring the phase angle between 2 signals. That's a different kind of.
If the sun was putting out so let's go to Cassiopeia, which might be a 1420 source for me, and a point-like source as well. Then I could have phase differences, and I would go below the baseline. Is that true?
No, that's not true. You still have the same situation. You have a continuous source, and you're measuring power and detect how does the power fluctuate. So it will go up and down as interference comes in, but it will not. There's nothing like negative power, and you're still measuring power. And our detection method is we have 2 signals, and we measure a phase angle, and of course the phase angle goes through positive and negative, so it's all the full circle. It's just a matter of how do I detect a interference pattern. So in your case, you're looking at the power, which is fine. It's probably a bit less sensitive, and we are looking at a phase angle, mathematically, essentially, by doing it on a computer.
Very good. I'm starting my education. Thank you very much. And
leave that on for.
question.
I got a question for Wolfgang on this. We had a big discussion. I think you weren't online one time. If so, the assumption is that peak center signal is when the sun's directly in line. And how would you plot that? Do you consider that the fringe spacing is the beam width of the antenna at that point, or how would you? I mean, what would you consider the resolution of that picture?
I mean, you have the overall curve, which is showing the pattern of the antenna, and I think Ted has explained that exactly. Yeah, that is exactly the pattern of one beam.
Right.
And then you have the fringes, which of course have a maximum when it is at the center. So if both antennas are pointing directly at the source, it has a maximum And obviously you can determine the location more better if you have fringes, so it's a narrower peak. However, to be on the safe side, you would have typically, in order to, if you want to do, let's call it real interferometry, where you determine the position more precisely, you would need a third antenna and see where all three you would have three antennas with somewhat different baselines, and where the three peaks match, that's where the location is. But anyway, I mean, this is it's a first step that you do, and we are not doing anything more than ourselves with just having two antennas as a start.
All right.
Now, Wolfgang, help me out as I space out my antennas, let's say to 4 meters instead of 2 meters. What should I be seeing? Fewer fringe patterns inside the envelope?
More. You have
more.
You would have twice as many. The overall structure would remain the same, because that's determined by the beam width of your antenna, but you would have more fringes in one pattern. Yeah.
So that would fill out my envelope more.
Yeah, that would be getting closer. Yes.
Yeah, your fringe spacing is divided by your baseline, your wavelength divided by your baseline. As you double your baseline, then you get your fringe spacing goes to half of that. And that means that you need twice as many fringes to fill in your entire picture there.
I think the question that was posed a few weeks ago was, what happens to this when you look at a diffuse area like the Milky Way H1 clouds?
You don't see any fringes because it's maybe one way to explain that is if a one-point source, you get a distinct interference.
Right, it's pattern there in his plots. It's right there in those plots. It's just a rock.
It doesn't show any fringes. It's just power. And I think a good way of explaining why do you not see fringes from hydrogen is think of a point source like what we're looking at in this case with the sun. Then an extended source means yet another source beside it, and yet another source beside that. And these would all give fringe patterns which have a different phase. So they all smear out essentially. There are many thousands of different fringe patterns which overall don't give a fringe pattern because it sort of smears out. That's the reason why you don't see any interference patterns. And that's also, by the way, there is no interferometric survey of the hydrogen distribution. Such a thing simply cannot be done because it's an extended source. The resolution that you have for the hydrogen distribution is determined by the single dish antennas that the survey was made with.
The cloud is too broad. It's even wider than the sun. Yeah, okay.
Yeah, it's so you're getting, in theory, you're getting many fringes from many spots, but they all have the same, more or less same brightness. And therefore they all give a fringe pattern, which is looking different from the fringe pattern from its neighbor. And all those many fringe patterns are even out to some broad thing like what you're seeing.
So by using a like Ted's interferometer there with hydrogen, we're just increasing the gain, but not the overall beam pattern.
Yeah. You're increasing the gain because you have two antennas. They give independent signals. So essentially, you're doubling the aperture, the receiving aperture.
Okay.
Just like building a bigger dish.
Okay. Now, if you put it far, let me ask this question about gain. When you put the baseline farther, does that improve the gain, the overall effective gain of looking at the Milky Way, or is it's just the fact that I've got two antennas, almost any distance gives me that gain no matter what?
Yeah, for hydrogen, it wouldn't matter what the spacing between the antennas is.
Okay. Great.
So my with wider spacing, I would get better spatial resolution of pinpoint sources,
That's correct. Yes.
even if they are on one frequency. I think so.
Yeah, that's another point that you're bringing up. What is the bandwidth that you should be using for interferometry?
Okay.
If you have a source like the sun or Cassiopeia A, these are broadband sources. So in principle, if you widen the bandwidth, you get more energy, you get a better signal to noise ratio. However, for interferometry, the trouble is that if I have one frequency and have a neighboring frequency, the interference pattern is different from the two frequencies. And if I make too wide a bandwidth, then again, the same is as with a distributed source. The different interference patterns, they don't overlap anymore. They just smear out and you don't get any fringes anymore. So you have to do a compromise between not smearing out. That of course is also dependent on your antenna separation. The bigger the antenna separation, the narrower the fringes are, the less spectrum you can use. And on the other hand, you just have to think about it. What's the optimum bandwidth? By the way, the interference pattern that I had shown, we were using a 4 megahertz bandwidth. I think there was in the chat, there was a remark from Bruce. I think he wanted to have a few comments on that.
Yeah, go ahead, Bruce.
Didn't have the mic on, Bruce.
Hear me now?
There you go.
Okay. With the chat boxes open, apparently kills the mic. But anyway, about 10 years ago, I had a interferometer going on 408 megahertz with two dishes, one 3 meter and one 3.7 meter dish, about 10 meters apart. And it was a phase switched interferometer, which Wolfgang's very familiar with. But anyway, that's a very effective way to get it with a simple analog receiver. So anyway, I had that going. And for the curiosity of it, I said, I wonder if this can detect the moon. So, 3 meter dish at, 400 megahertz is, pretty small and pretty broad pattern. And the moon by itself is, totally invisible. But I did see interference fringes from the moon. And as the way I kind of verified them is I looked a whole bunch of days in a row, and I would take the graph and I would, kind of synchronize it to lunar time rather than sidereal time so that it lined up. And the antenna declination was moved from, day to day to, get it. And so I actually had a whole stack of little fringes that were pretty rough looking fringes, but I was actually able to, see fringes from the moon on that. And normally you'd say, 3 meter dish moon, not detectable at 400 megahertz. But in fact, I definitely was, able to see it. It took about a week worth of, things to verify that I, you see a whole bunch of fringes that are the same or have a common component. You can see it with your eye. But if you just look at one of them, it's questionable. Is there a fringe there or not? It's real questionable. But anyway, that's the experiment I had run with, moon 408 megahertz and phase switch interferometer. So interferometer is a very valuable, mechanism for seeing weak sources in the galactic background because it washes out the galactic background on a phase switched or a true multiplying interferometer, and that leaves just your something that's essentially a point source at the frequency. If it gets wider than a point source at that frequency, it disappears.
I think Bruce has made a very important comment. That is that with interferometry, for an amateur side, the main thing here is that you gain tremendous sensitivity for single sources, or compact sources, I should have said. As Bruce had just explained, that's sometimes very difficult to see a continuum source in just looking at the total power. But if you do it with an interferometer and you see the fringes, that's much more easily detectable. So it's a very valuable thing to do, very interesting thing to do.
So can I ask a question about this graph that you have up right now? The peak, goes up at a certain point and then it dips down, and that's the fringing or the overlap of the two signals, I guess. And so depending on the system's quality, that peak is going to be, that differential from the top to the bottom is going to be better and better, I guess. Isn't that right? But the two kind of get washed out because the intensity gets so bright in the middle, and that's why it rises on the bottom part of the peaks. Down at the bottom of the graph. Yeah, those.
According to one book, the bottom is rising because we have an extended source of 0.5 degrees, and it doesn't get down to the bottom again. That's the reason it doesn't go all the way down with this kind of a source. That makes sense? It's called a
yes, definitely. That's the reason why you don't go very down to zero.
And then, so as that object gets larger and larger, those peaks get smaller and smaller to the point where you just have this overall 32-degree rise when you're trying to look at the Milky Way.
Yeah, that's right.
I guess the other debate we were having when Ted put this on his chart of when he was doing the on your survey, Ted, when you were showing where the big bump is, where the Milky Way goes, where it goes across the Milky Way, and whether we can reduce the not on this chart here, but basically whether we can reduce the size of the detection to smaller resolution on your chart if the phasing does that or not. And I guess the answer is no on hydrogen. It's not, it's just like having a dish, but it's just a bigger dish with two smaller antennas. Not that we got,
and that's because the source is so broad in the sky.
Right. So that makes sense that we just, it'll still have the same beam pattern based on the 37 degrees or whatever your.
So for finding the galactic plane in the sky, interferometry doesn't really help me, other than adding two receivers that are receiving. So yeah,
you got better gain, and that makes sense now. Okay, and I guess a follow-on thing about this filtering for Ted's now, if he wanted to improve this, he put a band pass filter in that reduces down to X number of megahertz recommendation. And I don't know, you don't have the filter in there now, right?
I think Wolfgang wanted me more to receive the phase and compare the phase of the two antennas.
But if you put a filter on each antenna or on the output of your combiner there, and then you put a filter there, I guess the question is, can we improve your system with filters?
I guess that has something to do with the RFI, the situation that you have. Of course, every RFI signal that comes in will, give a distortion or a disturbance of your signal. And
but forget the RFI for
a second. I really don't see RFI up here, so I don't think that's my immediate problem. I don't think filters really help. These Sawbird LNAs already have a filter in them, and I don't think that particularly applies here, Rich.
Well, I was just saying improve the fringing by reducing your actual frequency you're looking at and making it more narrow on each antenna would that improve the fringe, the signal? Because right now we're saying it, if we have too wide, then we get this overlap of fringes that wash out the fringing. But if we have very narrow, we're detecting very narrow on each antenna, our fringing should be sharper.
The bandwidth that Ted is receiving is actually determined, I would assume, by his SDR. So if he's using an RTL SDR, he has something like 2 megahertz, 2.5 megahertz of bandwidth.
That's 2.4. That's correct.
Yeah.
One of the things that can happen on an interferometer that I didn't do the experiments, but found it by paper, internet research. If your bandwidth gets too wide, is what happens is that the fringe at the frequencies at the low and the high side of the bandwidth, the fringe rate will be different. So your fringes can possibly wash out some from having too wide of a bandwidth.
Yeah, that was I was referring to. You have to compromise by saying, okay, I want as much power as possible, so I want to increase bandwidth, but on the other hand, I need to make sure that I don't decorrelate because of the different fringes, that the changes of the fringes with the frequency. And
so
we did
I'm using 2.4 right now, 2.4 megahertz, and I see fringes. If I reduce that somehow to make a narrower reception, I don't think it's going to make much difference, correct?
No, not in this case. I mean, by the way, we did some experiments to that extent, saying we changed the bandwidth, and our standard was 4 megahertz. We reduced it to 2, which, as we expected, because it's already a very narrow bandwidth, just reduced the signal to noise by a factor of 2, because we only had half of the power. Then we increased the bandwidth, and it looks like this is something we still need to investigate. We had a cutoff at some 6 megahertz were okay, at 8 megahertz were no longer okay, but we believe that this is an instrumental artifact that for some reason in the digital post-processing we had some kind of decorrelation. We still need to investigate that, because we think that 8 megahertz out of 1420 megahertz is still a very small fraction. But again, at the moment our choice of bandwidth is 4 megahertz, but that may be not the last word on it.
Another comment there that everybody seems to think on an interferometer you have to have your antennas on an exact east-west line, and your cable lengths have to be exactly equal. And in fact, both those things are untrue. If the east-west component of whatever their distance is between your antennas is what will make the fringes. So you can be quite a bit off on the north-south direction and not really bother anything. The other thing is, if your cable lengths are not equal, there's actually a kind of a formula for that professor in University of Scotland gave it to me from an email. But anyway, said if you have if you have 1 megahertz bandwidth, you have a certain correlation factor in there. And if you have a microsecond delay difference between the two antennas, you'll pretty much decorrelate things. However, if you have like 1/10 of a microsecond difference between the delays from the two antennas with 1 megahertz bandwidth, that will not be significant. It won't affect your fringes at all, other than moving the position of them. But it won't stop it from fringing. It will just move the fringes over somewhat according to what the phase difference of the cable is. So that's a useful thing for somebody that's putting something up, because no, you don't have to match the cables. If you're wanting to put a bunch of things together and correlate them to make an image, then you have to have your exact timing compensated somewhere along the line. But just getting fringes, you can have a rather large cable difference and still go happily along.
Yeah, our cables were not phase matched for the experiment that I've shown. We just took 2 cables which were sort of the same length, but they were also of a different cable type. So the delay and the cable will be different. But for just getting fringes, that didn't matter. If you want to go a few levels deeper, then you want to have phase matched cables and stuff. But as a start, just use reasonably close cable length. That'll do it.
Now, Wolfgang, we've been talking about three different kinds of sources. One is very broad, like the Milky Way up in the sky. The next one is the sun, which is half a degree wide. And then we're also talking about Cassiopeia, which we can consider a point-like source in the sky. What will Cassiopeia look when I put up my antennas on here? How will this graph change?
It would essentially not change other than a signal to noise ratio. I mean, you have.
Sure, it's a weaker source.
It's a weaker source, and that's it. I mean, you still have the same situation.
To get more precise spatial resolution, I need to actually add the phases and not just add the wires together.
Well, it's what we are doing is a measurement of the phase. It doesn't necessarily give you a better resolution than what you are doing. In order to get a higher resolution, what you need to do is increase the spacing between the antennas.
Now,
and as I said,
and yet when I increase the spacing with the way I have it set up now, all I'm going to do is get a broader envelope all around with many more fringes.
Oh, the envelope should be the same.
That doesn't really help me.
The envelope should be the same.
Okay.
Because you have more fringes, it will be sharper. However, I would caution that in the sense that determine which is really the highest peak from the various fringes. In order to do that, it's really advisable to have a third antenna and correlate all three of them, that correlate the different baselines.
Well, I have the equipment. I'm going to start doing that as well. I thought I'd start off easier. I was hoping I would get more of a sharp spike out of something for measuring spatial resolution, but I'm deflated here today because of that. All I'm going to get is the envelope spread out or filled in.
Yeah, you get the envelope filled in. I mean, with a 2-element interferometer, you're gaining sensitivity, but it's gaining. You're still interpreting the exact position by the maximum of the overall envelope.
Oh yeah, okay.
Yeah, and that's and
still pretty broad.
It's still pretty broad, and in order to get the ambiguity out of that, that's what you need to do is have at least a third antenna, and then you have fringes where you have one point where actually the 3 peak fringes match. That's the whole idea of it.
Now, can I take those 3 antennas and take their center conductors and short them together and send them into the house with that kind of combiner? Will I see a sharper resolution up here?
It's a pretty crude setup. I don't know what that will be doing with phases and stuff. That's
well, I'm adding them analog way, I thought.
Yeah, but if you just, I mean, it's
when they're all positive, they add together.
Yeah, but you have reflections and you have discontinuities on the cables and so on. It's a fairly undefined RF combining, and you don't know what is happening with the phases there.
Okay, I agree with all that. Yeah,
I think
I'm going to start with equal length cables pretty much, and we'll see what happens. Yeah. There's somebody else, Rich.
Yeah, Ted. I think the answer your question about the your point source that you can detect, not the Milky Way, but the sun. Remember, we were talking about that whole bottom is lifted up because you've got an extended source. The Cassiopeia, theoretically, all those should be flat on the bottom when you're done with the point source. So you won't get that bottom, hump there on the bottom fringes.
That's interesting, but not really exciting.
I know that. I didn't say it was exciting. I just said you want to know the differences.
I'm looking for spatial resolution so I can find things in the sky. Yeah.
Based on my little model I did in MATLAB with a third antenna, the only you won't get this nice pretty fringe pattern unless all 3 antennas are dead on at the source. When the source passes in front of them, they're all equal. Then you'll get that top hump. Otherwise, you get what Wolfgang was saying. You can get all sorts of different fringing going on that's not as pretty as this. Until it hits, they're all pointed at the same time. Then you're going to get a larger.
So I'll get one peak that's higher in the center.
One peak that's higher by 3 antennas worth.
Okay, well that changes my envelope here. Then that's good, and
No,
that's all.
envelope stays the same. They're all the same beam width.
But you're not going to get this smooth
You want to get a nice pretty
cosine type shape. It's going to be, you're going to get strange variations along that path.
So it's going to be bumpy with side.
Yeah, you may get one big one in the middle, but you're going to get strange things all on the sides. Because you have
as long as that one's in the middle, that improves the odds or is a multiplier for that part of the sky. So yeah.
Could be.
Yeah, well, what you want to do is have different correlations. You have 3 antennas, A, B, C. So you want to do the AB correlation, you want to do the BC correlation, and the AC. And they all give a different fringe pattern, which is measured separately. And then you look at how does the fringe pattern overlap? And in theory, there should be one fringe from all the 3 correlations, which has the same peak at the same, or has a peak at the same location. That's your location where the source is.
And I think we're playing with Fourier space, Fourier transform and such.
Yeah, that's another story.
So
with
imaging.
So that would be the very first step of getting a more precise localization from 3 antenna. And when you have more antennas, then you should talk to Jim Abishir, I think, how is it pronounced? Because he's really the expert on that, and he has been at the top level of these things. So he has done the real stuff.
Right, now we're approaching the VLA, and I'm not sure I quite have the funding for that, but okay.
Yeah, I mean, the thing that he did was, if I remember correctly, was it 3 antennas or maybe even more, which were not VLBA in the sense they were locally correlated. So he had one clock source, but he did the real thing, going through all the processing of getting finally a precise localization.
And another question on the placement of the 3rd antenna. Would you have, so you got an east-west baseline, would the 3rd one be the same distance and baseline on the north side, dead center in between the 2, from an east-west point of view? Is that where you'd put it?
You would put it also on the east-west baseline, but at a different spacing, not a multiple of what you have already. Some strange parameter, I would say.
Huh.
So let's say if now we have 2 meter, maybe I would put the other one at 4.50 meters or something like that.
Oh,
and
okay.
You're suggesting on the east-west line.
Yeah, on the east-west, yeah.
Why not north-south, as Rich's paper at the conference talked about?
Because you could certainly do that, but it's getting more complicated, saying, how do the fringes work?
I think Wolfgang's going after a particular, what do I call it, meridian across the sky, from the zenith down to the horizon someplace, and increase the spatial accuracy into that line. And Rich was trying to figure out where on that Verizon, not Verizon, Zenith, the horizon line, where along that line it was. And so I think we're going after different goals.
Well, mine was a theoretical, can I reduce the resolution in the north-south as well as the east-west by combining those fringes north and south and east and west? That's what the thought process was there. And I guess by putting it on the east-west, another one on the east-west, and it's a different sort of a correlator. It's sort of it gives you a different fringe pattern between, but you have to measure them separately, right? You probably just can't combine them all 3 together. You have to measure them, first A to B, and then A to C, and then B to C. separately and then combine them. I think that's what Wolfgang's talking about.
Yeah, but what I would like to do is actually have a third antenna and correlate all of them. The thing that I'm missing at the moment is an STR that has 3 inputs which are phase correlated. That's something but at the moment I'm for the time being we'll stick with the 2-element interferometer and play with it and learn it, go through the learning curve, and then take the third antenna eventually.
And at this point, there's nothing you can do to combine signals before you put it into your receiver, correct? You want to actually get the true antenna's phase.
Yeah, there are different ways of doing it. I mean, one of the things that were done in, let's say, at the times when things were mostly analog was what Bruce has described, the phase switching interferometer, which essentially is you have a signal path from both antennas, and correct me if I'm wrong, Bruce, but I think you insert into one of the paths a delay which can be switched back and forth, in and out.
Okay, all right. That's
So
getting close to analog.
Yeah, that's correct. In my case, I was actually using a mini circuits labs mixer as a phase shifter. So I have the one antenna goes straight into a summer. The other antenna goes through this mixer where the IF port of the mixer is DC coupled, and I drive it with a signal. So if I drive a DC one direction through the IF port, it's a 0 degree phase shifter. And if I run the same level DC through the opposite direction, I have a 180 degree phase shift. And that proved to be very effective. And other methods that I tried to put together had trouble with gain matching, because when you switch your phase by 180 degrees, you want the gain to stay exactly the same. And the balanced mixers, because they put a lot of effort when they manufacture them into getting a very good balance, it says you see very little difference in gain. It's almost unmeasurable when you switch the 180 degree phase. And by the way, in my case, I was switching at 512 hertz switching rate, switch back and forth. And then the output of the receiver, you have to, synchronously demodulate that. But if you do that, it's very important to avoid multiples of your local power line frequency, because any noise will get kind of an extra correlation boost on you. Whereas if you're not a multiple of the power line frequency, the power line noise spikes that come in tend to get washed out. End of comment.
Thank you for the comment.
I think the advantage that we have these days is that we can do the correlation on a digital side. So we just digitize a signal as a complex signal, INQ, and then the rest is math, which is done by the computer. And the computer these days are powerful enough to do that on the bandwidth that we are typically using. That takes a lot of hassle away. But of course, still the phase switching interferometers is a valid approach. The question is essentially, what are the things that you have on hand to implement things? And in our case,
you could actually have a slider that adjusts the phase in your software, Ted. You like to do the software side of it. So you could add your signals at different rates and look at what happens to your graphs.
My problem is I only get one signal down one coax. It's already been combined.
Yeah,
So,
you'd have to split them up and have two signals that are clocked at the same rate.
well, that gets tricky at the receiver side. Yeah. So I was trying to cheat.
And
all right, very good.
To do that on the RTL SDRs, you can do that, clock them together.
I've seen that.
Mm-hmm.
I think, Ted, what you're doing is what is called, I think, an adding interferometer, which is a valid approach. It's probably not as sensitive as you can get with other instrumentation. But anyway, it's fun playing with it, I guess.
I've begun my learning process. Exactly. And thank you for your help, Wolfgang. Very good.
Yeah.
And Bruce.
Wolfgang, on your use of GNU radio, sometimes there's a resampling function in there, and maybe that's where some noise at some strange frequency is creeping in. And for the signal switching at the power line, what I've tried in the past is a sneaky filter, but which A to D converter, I take 0 crossings of the 60 hertz and or 180 or whatever it happens. Actually, 60 will do. It's a slow sample, but if you use that as the clock for sampling, it's pretty accurate, and you're always sampling when the power line frequency is going through 0 crossing, so there's no voltage from it to get in to cause noise at the power line frequency. Oh, and I have
unfortunately the 3-phase line running in front of my house, they've got arcing hardware. It's going to be arcing throughout the cycle. So trying to use a 0 crossing is not effective if you have any 3-phase power near you.
Gotcha. That's quite true. And as an armchair, I have something here. Maybe I can show it to you.
I'm scared with what Rich is doing, though.
I was going to show you this thing, but I had my mute on, so I wasn't able to explain it.
Why isn't this working? Oh, God.
Oh, because you got your background.
There we go.
On. There you go.
There we go. Can you see it, everybody? This is
Yes, we can see now.
This is a very good book.
Oh, look, we got in stereo.
All right.
That's it.
Rich has got his out too.
Okay, so I want to explain what sort of like the kit, the teaching version of the thing is. When you get the kit for the itty bitty telescope, you see this? It has a Lazy Susan on the bottom of it. So this is what Tom Crowley produces for the itty bitty telescope. All right, and so you have this thing, so you can turn it. Well, the way the
and that's with the single antenna on the top.
Yeah, that's what single antenna on the top. What I did was, according to the book I gave you, what he did is he actually had the source. He had a test source in front of this was all inside, had a test source stationary, and he moved this to simulate the horizon moving.
Very good. Lean it back a little bit, and they can see their Yagis.
Yeah, I got 2 800 megahertz Yagis there. That's what I found. But I have to. You get like an 800 megahertz source, little test source. You put 10, 15 feet away, whatever you can do inside.
So I've seen a test source is be simple as one of those fluorescent compact lights. Apparently, it give out a bunch of high frequencies, and that was convenient and point-like.
And so you measure as you angle this thing, you measure the degrees change against that, and it'll simulate your fringe pattern, and you'll have control over it. So that's what I was trying to put that together. Haven't done it yet, but I've got it on the Lazy Susan, and just got to calibrate the angles and get this thing to do interferometry inside, and it purely is a teaching tool.
Cool. We want to see your results.
Cool.
Okay, that's just a thought.
Where did you come up with 800 megahertz Yagis, though?
I don't know. I didn't know anything about fringe patterns when I chose them. So I think that
they are cute, though.
I did look at that.
Good old Amazon is chock full of them.
Yeah. I looked, if you look at that book I gave you, Ted, by Lonk, he has something very similar to that I got the idea from. It has a Lazy Susan, and he has a source inside, and he basically makes the fringe pattern by moving the antennas on the Lazy Susan with a stationary fringe in the front. And it worked great. It produces that nice pattern and tests all your stuff out.
Now my question is, so where do those two antennas go? Does he have two input receiver, or did he combine them like I did?
He's combined them just like you did.
Maybe with a TV
Yep.
split or something. Yeah.
That's, yeah. You can also do that as a double slit experiment with a couple of microphones and a speaker, or you can do it with a light beam and a couple of and a couple of slots, and it's all the same math.
Makes sense.
Yeah,
Rich is muted.
it's a double slit. It's the experiment. It's a double slit experiment. It's just done at RF or at acoustically, or I mean, we did that one acoustically in my freshman physics lab, but I hate to tell you, but in 1960, and that was a pretty long time ago. I don't remember it very well.
They had speakers back then. That's good.
It was only analog back then, right?
Yeah, it was all analog, and yeah, the speakers were these big horn things, you know.
Neat.
And we're not talking about the vacuum tube amplifiers you had hooked on the end of it either. So, okay.
No, it was tubes with you put them in your ears.
Oh, okay. Yeah,
And
just
tube,
with plastic tubes, that would work.
Yeah, you just could maximize by just listening to it, you know. No, that's not really true.
I like it.
Okay. All right. Let's see what else we got. Okay. Are you done, Ted?
I think I'm done. Thank you for your patience.
Great. I think this is great stuff. This is all for us to get into interferometry. I think all this is sort of coming to people could start doing it.
These are the learning pains. Yes.
That's right. Okay. Alex, got anything?
Actually, I do. It's on a non-interferomic system. Let's see. I have been going back through my software and trying to clean it up and add a few features to it. And I put a slide set together in case people aren't familiar with some of the processes. At least these are some that I have implemented. Let's see. And kind of shows off the capabilities of my my current scope in the box. I don't know if that's even the proper title for it anymore, but I wanted to show you what I have been doing. Back in March, I ran some 24-hour drift scans, and I've never processed them up until a few weeks ago. Can you see this? My PowerPoint
looks great.
Yeah.
Milky Way neutral. Yep.
Okay, so, well, okay, so I'm going to go through this, but this is what I have set up now. This is my MATLAB output, and the top 5 are basically diagnostics to look at the processes that are going on, and that's what I want to discuss. And the bottom 2 are the outputs. And so this is the path that I have implemented. The first is cold sky correction. And we have the original data, the baseline drift, and then the output out of the correction factor. And the way this works is, what I did is I took 40 channels, 40 samples, 40 frequencies out of each one of it's like 270 records or files. And I did a mean over about 40 samples, and I got those values. And this is a plot over 24 hours. And what's interesting about this is that's when I went out in the late of the night and I put a polyethylene tablecloth across the whole dish because it was getting heavily dewed. And this is probably me installing the tablecloth, and so this shift is caused by the tablecloth. But what's interesting is the software corrects all this stuff pretty well. So the cold sky is the mean of all of these, and so that contains like 270 elements. The next is to find the minimum of that, and so cold sky minimum is this value, and that probably correlates to this time. I don't know why it got so low, but that's what's happening. And so this is what I find is the very lowest reference, and then go through and take that value. And the process here is to calculate this lowest minimum from all of the other samples, these cold sky values, and normalize them together. And what you wind up with is a plot that looks like that. And it's gotten pretty good. These peaks now are about, the cold sky to peak is about 3.8 dB. So the little scope in the box has got some pretty good quality amplification or resolution now, signal noise ratio. And just to show you that this is not filtered data, one sample had this spike. And I'm almost wondering if this was perhaps an aircraft going over or a helicopter. I don't know why, but one showed some interference that isn't on any of the other sets. So this is non-filtered data. It's 5 samples. So the other half of this is, and this is much more complex, but this is the local standard of rest velocity correction. And so you take the set that's been corrected for baseline drift and then process it by this VLSR curve. And so the idea here is you have to use some software that can derive the VLSR correction for the data set that you are acquiring. And that includes the location of your radio telescope, the position of your antenna, and the date and the UTC for each sample. And then what you do is each sample is corrected by subtracting its corresponding value that has been calculated, and you wind up with this. And so this over here is the uncorrected data for the drift. And over here, this is showing the correction after it has been corrected for velocity. And what you're seeing here is the Earth swinging in and out of, going towards and away from its orbital velocity. And these velocities are around 35 kilometers a second. And so this is like, in the afternoon or in the morning, and this is at night, because you're swinging through the rotation. As the Earth rotates, you're swinging into and away from the axis of rotation. And so this is what this looks like. And with this, you can take this data and create a contour map. And this was what you're looking at is this swing through this part of the sky at declination 40 that you go through part of the Milky Way. You never really get out of it, and you swing back through the other side. That looks like this. It's pretty interesting because you can really see the near arm, and this may be a smaller one, and this outer arm here are nicely defined. And it's pretty high quality data for a 1 meter telescope. And then you can also take a look and see the effectiveness of the VLSR correction is pretty dramatic. This is what you would wind up with if it wasn't corrected for the velocity. And the other is to take a look at this in a 3-dimension surface plot. And what you can see here is the sinusoidal curve of the VSLR correction, where these would be skewed in velocity due to the Earth's rotation. They're nicely aligned up right now because of this correction. And if nothing else, it's almost an art form. This looks kind of, so this is a radio telescope art. And so that's the story. Any questions?
So now Ted's data, Ted, the data you're collecting is you're just doing total power for your measurements. You don't need to correct it for velocity. Is that correct?
I go through all the same steps that Alex has. I approve of all the things he's doing there. I correct for variation in gain. We think that's mostly due to temperature changes over time. And then we play with VLSR and change the spectrum. And so I get kind of wavy lines on my graph as well. You were showing some down on the ground kind of curving around. And so all of this looks very familiar. It's gorgeous. And of course you have more frequency bins, frequency buckets, different channels than I've been using the 256. I'm just making my files smaller that way. And so it comes out with much more detail, which looks great. I do have one question. Let's see, back at, you picked 40 different frequencies and took the average of them. Well, how did you pick the 40?
This was probably a year and a half ago when I first
back in the beginning, yeah.
When I first
began,
when I first began doing this, putting my software together, I just picked some frequencies at that time that were not influenced by any of the hydrogen spectra. So
so non-hydrogen frequencies.
Yeah, any of this that you get near the edges, you get some weird edge effects. So I just picked any, and it was from channels 80 to 120, and that was totally arbitrary. And I might be getting a little bit close here. It may be the VLSR frequency shift is a little bit on the borderline, but the results look good. But yeah, I took the mean of them, so it helps to reduce some of the noise, and I just picked 40 channels. And this is sort of a trial by fire here. If I can correct for this craziness offset of me and the tablecloth, it does a pretty effective correction.
You were changing the gain of the antenna by putting on this tablecloth.
Yes. No, it's not gain. This is not gain. This is a change in background noise. This is not gain. This is an added noise. It is measuring a little bit of none of this is gain. This is all background noise. This is the cold sky lifting up.
Neat. Okay.
Okay. Also, I did want to show you something here about, I know you had, let's see.
I like that.
Well, is that cool?
Yeah. Very nice.
What I wanted to show you is this is the variation. I went through the process that you had been using in saying, okay, all the variation is due to gain, and so you divide it. And so this is the plot that I got with the same configuration doing gain variation versus assuming that it is a baseline shift due to the sky transparency, who knows what, and this is the difference. And so I'm still going to say with the noise level is a background shift and subtract, but for your benefit, I did both.
Oh, thank you for that, because I'm kind of still on the fence. My division.
Well,
and subtraction actually probably makes more mathematical sense.
Let me show you this. If you recall, I think you were there when I went through this Saulberg gain drift measurement, And so of these two, I just picked, let's say it varies by 15 degrees and it's about 0.15 of my variation here. This is all that you would expect to see from a sawbird over, what, 30 degrees Fahrenheit variation. And so this stuff, whatever's happening, to me, I believe this is, I don't know if it's moisture in the air, if there's reflection of the sun off the trees. I have no idea. But at least in my case, if you exclude the tablecloth, these variations are much greater than just a gain change. And so I would recommend trying to do a subtraction. Need to be in power. See, that's the one thing with the IF average. It originally, these are not power units, they're linear. So you have to square them because random noise amplitudes add or subtract as their power. And so first thing I do is change everything to power.
Very good. I agree. I wonder if the temperature gain, the temperature variation is also changing some factor of the coax or connectors or something.
But I
don't know where it's coming, but it's remarkable how quickly it will change.
Yeah, see, I don't know if I have it on this. Every chart I have done, well, this is part of my processing, and I display this for every analysis that I've done. And there are some very dramatic changes that make absolutely no sense with excluding this tablecloth. And so I can't correlate that with gain because I keep the LNA is right at the antenna. And so beyond that, you have basically whatever happens after that, the gain, the effects of a coax or something like that would be reduced by a factor of the gain of that LNA. So it's like a factor of 40 dB, factor of 1/100th of what the power would be. And so I don't know, but let me see. I don't know if I have this on this slide.
I agree. I don't know where it's coming from, but boy, does it come. Yeah.
Yeah. And so, like I said, I really think it might be worthwhile taking a look at your data and trying the subtraction method. I mean, to me, it looks nice. And so.
Yeah, the subtraction just looked noisier to me. So I kind of moved down a different path.
I'm going to make a suggestion. Take
Yeah.
longer averages. Don't take 15-second averages.
Well, but I'm worried about spatial position on the sky.
But look at this.
I don't think you've
this.
addressed that quite so much.
This is 5 minutes. I mean,
okay.
I don't see any spatial.
I think you have some averaging and shaping going on here, but I agree.
There's no averaging here. I mean, I don't know that MATLAB is, I don't know what MATLAB does, but this data is not averaged in any way. And the proof of that is this one frame having this erroneous signal. If I had filtered it, this would have been attenuated. And so all I'm saying is this is some nice resolution. And though these steps show the spatial resolution of as the sky drifts by, and I certainly don't feel that I'm losing fidelity and amplitude versus gaining a really nice signal noise ratio.
All looks great. My other question was about VLSR. You had a graph where you calculated it and had the nice sine wave.
Yeah, that's from
that one in the middle. It's interesting that yours starts right at 0.
That just happens to be that day.
Yeah.
It just happens to be the 30th of March at UTC is 1700. I mean, it's going to start as you go through the year, and whatever time of the rotation of wherever you start your data, it's going to be anywhere in between this.
So I would expect that sometimes is offset from 0, the whole thing. It might be more negative in general than positive and such.
Well, the VLSR correction The VLSR correction is dependent on your direction of observation. Essentially, the number one component to your VLSR correction is the motion of the Earth around the sun. And as you do an observation, you're looking at different directions, which means that the vector of the motion of the Earth compared to the vector of your observation will change over time, and therefore different parts of the velocity of the Earth around the sun will add. And on top of that, of course, there's the rotation of the Earth itself, which is in the order of maybe 1 kilometer per second as a correction, and then there's some more minor things.
Yeah, it's like plus or minus 0.4. So
yeah, 0.4. It's 40,000 kilometers roughly divided by 24 hours. Yeah, but if you depending on how you do your observation, let's say you're looking at a fixed position in the sky and let the right ascension be turned by the rotation of the Earth, and of course you're looking into different directions, and that will lead to different VLSR corrections, and they can be essentially, as Alex has pointed out, can be fairly large, depending on how you look and which
yeah, this was purely coincidental.
Yeah,
very good.
The only thing that might be misleading, it is not a 24-hour correction curve in the sense that if you're looking at the same direction all the time, that is what you will be seeing. It is if you have a sort of a drift scan, how will that vary over one day?
And this is sidereal. This is 23:56. 23 hours 56 minutes.
Yes, but you're looking then in different directions, correct?
Yes, absolutely.
It's not, yeah, that's the point I was going to make.
Yeah.
Because the contribution of just the rotation of the Earth, if you're looking in the same direction, would always be in the order of 0.4 kilometer per second.
Exactly.
But anyway, that's as you do a drift scan, then it varies like what you're showing. Yeah.
Excellent. Yep. I think of it as you're on the Earth traveling around the sun, and sometimes you're facing forward in the car and looking out the front windshield, and sometimes you're looking at the back. 12 hours later, you'd be looking out the back window, and so
yeah, that's
apparent velocity is different.
Yeah, that's a very nice explanation. Yes.
And the car is moving at 35 kilometers a second,
which will
Correct.
give you a speeding ticket anyway, but
the cop would never catch you.
It's the Audubon. You never know.
Thank you, Alex. That's a real nice explanation. Well done.
So
I enjoy putting that together. Like I said, the result is almost artistic. I was very impressed with the answer, with the final process of putting all of those the spectra together.
So if you sign and number those and you put them in the SARA store, we might make some money out of it.
I can do that.
Let's see. Okay, let's see what we got. We got 14 minutes. Anybody got something quick?
Yeah, I had thrown something on the chat, but anyway, I had seen a lot of the things from the Radio Jove loop of group of catching solar, flare-ups at 20 megahertz, and I said, well, I want to try to catch some of that. So I have an active antenna, active dipole for 20 megahertz that I've done some experiments with. But anyway, put it out in a single dipole, so it's small. But anyway, I can catch the solar flares, but I've had a lot of trouble with EMI. And it's kind of interesting that, some of it's at my house, and I think some of it may, at the weaker level, may be neighbors' houses, which is a little more difficult to handle. But I found an interesting thing in my barn/storage building now. But anyway, I'd gotten some light fixtures that are 4 foot long, look like fluorescent lights in size and shape, but they're actually LEDs that have a switching power supply in them. And those things make all kinds of noise. I mean, they virtually saturate the receiver when they're 15 meters away. So I thought it's interesting. So right now I'm taking one of them apart, and I do have some experience. I had designed some power supplies for LED lighting in my career, and one of them got to be a military application. And I think protecting a radio telescope is almost like a military application. But anyway, the supply I designed for a military application, I noticed that the power supply was probably almost one half of the bulk of it was EMI filters to keep it confined to military levels so you don't interfere with every imaginable frequency the military is using versus something that's made for a home use, which has to pass the FCC 15. But anyway, I took the thing apart and when I'm apart, and I'm rather appalled at the construction of it. It's definitely doesn't look like EMI was anywhere near their thought. It's barely past the legal standards and sell it. But that's about the end of the comments on that. That LED lighting, especially at lower frequencies, can be a lot of problems. By the way, I did try some of the just LED light bulbs that have some kind of switching power supply in them. And they didn't seem to have any problems. I can put them fairly close to my antenna and barely see the effect of it versus these, big lighting things that I got. They're humongous noise sources. So just a thought for somebody that's going to be trying to look for solar flares or radio Jove, anything HF, look out for the LED lights. They're out to get you.
All right, great. Thanks, Bruce. Rob, you're far away. Why don't I get you next?
Rob has been busy sending me data
Oh, okay.
from Australia.
There he goes.
Sydney.
Good morning. Finally figured out how to do it. Go ahead, Ted.
Oh, no, you carry on.
Oh,
What have you been busy with?
We've had the time change this weekend, and so I missed it by an hour. That's okay, whatever. Anyway, not really doing anything except letting the radio telescope collect data for Ted, and putting some things together, trying to figure out what the heck is going on. What I have done is I have bought several of the AliExpress or whatever they are, spectrum analyzers, and trying to figure out how to use those to find some noise in the system. But just learning about those things, and they're not expensive, but they seem to be reasonably good. I don't know if anybody else has tried to use them to find signal sources. Okay. Really, and also went out and now have the hatch and the dome are working, and I've actually transported one of the telescopes that I have out to the dome, and hope to put that in after I return from from California next month. I'll be in your neighborhood starting next Friday, and I come back mid-November. So we'll see what happens there. Outside of that, nothing really spectacular, to report.
Sounds like a list of exciting items, actually. But Rob, on practical matters, when was the time change? Was it last night?
No, Saturday night.
Saturday night for you. Okay.
Yes.
So within 24 hours. And Wolfgang, when is your time change happening? And how many countries go along with you?
I think it's somewhere around end of October. I don't recall the exact date. And all European countries change at the same time. And as far as I recall, it was 1 week different from the US.
Okay.
So either we are 1 week earlier, or you're 1 week earlier. I don't recall which one. I'll keep a close look, because I remember at one.
Most of the countries near Germany change at the same time.
Yeah, all European countries change at the same time.
Okay, so we got some real independent ones and want to do it 2 days later or something. Rich.
So I keep the UTC the same for the next calls, or what do we need to change the time? Just leave it alone?
I think we just leave the UTC alone. We just have to pay attention and sympathize and, be understanding.
Okay, sounds good. Okay, let me get the rest of these people real quick. We got 8 minutes. Helen, what do you got going on?
my, I'm overwhelmed as usual, but I'm like in kindergarten compared to you gentlemen. But I am studying and I'm learning and I'm enjoying what I'm doing, and it's starting to come together and making a little sense. So I'm just every day plugging away at it a little bit more.
Okay, great. And it's fun listening to what we had 5 different accents. If you count my Colorado accent, which I don't know what that means, but yeah, it's fun listening to everybody.
Well, I'm Hungarian, so.
Oh, there you go. Okay, thanks,
Okay,
Preston.
thank you.
I don't have anything this week. Thank you.
Okay, Don.
Just armchair at this point.
Okay, great. Bob.
Yeah, I'm working away on getting my system going to copy the WWV for the HAMSI group, which uses a thing they call the GRAPE. I purchased a Leo Bodner frequency reference, spent about a day trying to get that thing reprogrammed and figured out how to do that. It's not quite as easy as you might think to set it at a particular frequency you want, but they're pretty nice little reference for about $100. And I've got my other antenna set up to do the H1 measurements, and I got a couple of RTL SDRs. There's a new version 4 that I purchased and hooked those up to a computer, and that wasn't communicating properly. So I've got to sort out some issues there. And I put that aside till I get this other system working. I'm working with the GNU radio now, and I'm starting to see signals, and I just got to get it where it's recording data and uploading that to a general system that a lot of people are passing their data back into. So having some fun with all that. That's all I have. Back to you, Rich.
Great. Okay, and just close out. I'm probably going to put this up on the YouTube because I think it was a great session. Go to your chat. Dimitri has both articles on there, and they won't show up in our, once I turn off, they won't show back up. So go ahead and download those if you need them or you want them. And then I'll probably post this here in the next couple of days, put this up on YouTube. I think we got a lot of good stuff in here in this session. Okay, that's all I've got. Thank you very much, everybody.